Start recording anyways. Just give me a second. Right. So last test in Zoom. Do you see my screen now?
Yeah, we can. Thank you.
Okay, thank you. Oh, you're probably seeing a wrong screen. So let me see.
It's perfect. It's perfect. The metrics for future.
So you see only the presentation mode.
Yeah, correct. Yes.
Oh,
Full
good.
screen presentation. Yeah.
Good. All right. Hello, my friend. Good to see you. We met before, right? Like last year. So some of you took my course on knowledge representation and management. Is that true? Was it 2 years ago? Wow, time flies. Ah, right. So it's a different distribution of programs here. So okay, poll for belongingness to different programs. Who is belonging to applied AI? Applied AI only. Okay. So who else do we have here? Can you just cast names on me? Huh? Y program. Okay, Y program. Okay, nice. Do we have our usual data technique? Okay. And which program are you from? Hi, Erasmus students. Oh, great. Okay, welcome. Welcome to Erasmus students as well. And we have some distance students as well. Actually, this meets quite well my expectations. So normally I have mixed class in this course. And yeah, a little bit of history behind this course. So I developed this course for almost 10 years ago to be one of the first ones in machine learning courses. And it used to be a rather small course designed for 15-ish students. And after that, it grew to a rather large course, especially when a new AI program started. So I think now in total, we are around 80 students, I think, effectively. And that also was reflected in the modified course structure somehow. But this is an advanced level course, so you should expect quite some work, or so to say, deep dive into a particular area of artificial intelligence. So saying that, again, another poll for opinion, artificial intelligence, AI, what is in this acronym for you? So I guess you have some previous knowledge, but cast some words on me. Keywords. AI. Agents. Agents, sensors, actuators. But what is it we I mean, we will cover this topic in the second half. So, but what is it, in your opinion, we artificially recreate here? What kind of functionality? Huh? The brain. The okay. And just again, we're going directly to the focus of this course. AI is a rather diverse field of science or part of computer science, aiming at implementing intelligent functionality or functionality common to biological intelligent objects in or on computers, as easy as that. At the same time, so this functionality is rather diverse, as we will see. So here we are focusing on kind of first leg of AI, which is about sampling the environment. And so this focus, again, it can spawn a whole discussion whether machine learning is part of AI or not. So different people have different stance on it. However, and by the way, so again, saying that, AI versus machine learning, what's the difference?
Learn kind of a broader term for getting output without the procedure programming algorithm, and AI is like a subset of that.
Okay. Alternative opinions on that? Yeah.
It's the broader term, the also more philosophical aspects of what's.
And actually, I mean, well, this answers of yours gives exactly the correct picture of, people having different opinions about, I mean, what's put inside these terms. I think I tend to agree with you that AI is more a general term, and machine learning is a subset of methods, learning methods that is very task specific. So machine learning algorithms, so they're data-driven models that are trained to meet the performance requirements of a given task. For example, classification or prediction of the next value and such. However, again, so there are people within AI who think that, well, machine learning stands apart. Well, it is not. So it depends really on the context. In the context of AI, we talk about, as I said, a first leg of learning where we interface an environment. So you correctly mentioned that an agent is a fundamental concept of AI. So an agent is like anything, any artificially created or human-created software that operates in an environment, interacts with an environment via sensors, so it fills the environment, and be able to affect the environment via actuators. So here we are talking about the sensing part, and we will make a deep dive into what does it mean to actually process data with different kinds of algorithms. A little bit about myself. So I think some of you have met me before. So I teach quite some courses here at the university. My name is Evgeny, with the strong G. It's, and I have several hats on me. I'm a professor here. I'm also leading a group of researchers called computer science. So a chair of computer science. So at the same time, I'm also an adjunct professor at La Trobe University in Melbourne. There, I have several. I have a team of PhD students looking on high-level AI functionality, like LLMs and such. I also, since as of this year, I'm a part-time researcher at Ericsson Research, where I work in the area of my main focus, which is hybrid artificial intelligence, meaning that we are creating solutions that bridge the symbolic world, the symbolic reasoning, knowledge representation and management, and neural networks, so learning approaches. So I don't know, if for some of you it might be of interest. There could be some master thesis topics related to this work. So in the context of Ericsson, we are developing solutions for so-called native AI architecture. So and here is, I think, the part where or the application of AI, which will make the most effect, I believe. So streamlining the management of complex systems. So in the case of Ericsson, so you can imagine it is a mobile network with different operators, different actors involved, down to all the equipment over the out there in the field, requiring configuration and such, which fails from time to time. And in this case, this equipment should signal this error somewhere, and this error should be intercepted by special software, interpreted, and plan for actions on how to fix it. So still nowadays, there is a huge involvement of human operators. But the complexity is such that the complexity of the management task is such that it is very, very costly to have humans in the loop. So there is a vision of so-called zero-touch network management. So that's where this system, the mobile network, should operate totally autonomously. And this problem formulation is not specific to mobile networks. Take industrial automation. So Tatiana will talk about it when introducing her, or any other complex system. So it is there where we need intelligence, really, from the level of sensing and interpreting what is sensed, connecting to the knowledge and to analyze the situation and plan for solutions. So yes, but again, the focus of this course is to give you kind of slices of the recent advances in the area of data analysis using AI technologies. And this course, so now I should stop talking for a moment and introduce my colleague. So Tatiana, she is associate professor here in our group. And she will be co-lecturing and assisting you with the labs. So maybe you can introduce yourself a little bit, Sophia.
Senior lecturer here. And my research field is industrial automation. So like maybe I can help how we can shape your AI interest in the field of industrial automation. And I will provide, as Evgeny said, some lectures. I will like once in a week, next week, we'll have consultation sessions. You can join these consultation sessions. You can ask questions. What else? We will look through the lab's task. Yeah, that's all.
Mm-hmm. Thank you. And today, so basically, Tatiana will continue after the break, and then so tomorrow, the class tomorrow and the day after tomorrow will be given by me. And so then again, Tatiana will come and talk about natural language process or word embeddings techniques. Okay. Yes. Course material. Well, there are plenty of information out there. So again, it's hard to suggest a single book, and actually historically this course doesn't have a course book. So the material is a kind of collection of information from different sources. So you basically should use lecture notes for preparation. Well, you can find lots of information in this classical AI book, A Modern Approach to Artificial Intelligence. Any recent edition would work. As well as I said, so plenty of open courses if you want to get an alternative vision or better understanding of certain contents. Content and course structure. This year, the structure of the course got a serious boost, I would say. So I think those of you who you who took this security course, did you take it last year or this year? Last year. Okay, then it's also new for you. Since this year, so I changed the layout of the course in time a little bit by different reasons. Mainly because I want you to focus on kind of single task at a time. So we will run the course in kind of sprints. So you will have a theory week followed by a practice week. Theory week followed by a practice week, and so on. And here is the layout, a thematic layout of the course. So this week we will talk about fundamentals of machine learning and some important caveats when training machine learning models. We will talk about support vector machines starting tomorrow as the most mathematically rigorous learning algorithm, and also an algorithm on which several fundamental concepts can be demonstrated. And we finish this model by some models within natural language processing. So specifically, we will be talking about word embeddings and different kinds of word embeddings. Again, one of the practical points with this course is to show you that same functionality can be implemented by different means, by different algorithms, and the difference will be in the complexity of the solution. So basically, again, that's not applicable to you, but for a layman out there, when being spoken about machine learning or AI, so first thing that comes to their mind is artificial neural networks, deep learning, convolutional neural networks, GPT model, what you name it. Apparently, the spectrum of available models is large, and I think in many cases it is overkill to go for a more complex model like a deep neural network, for example. So you need to have an understanding why you would go one way or you would choose one mechanism or another. So and you will see this kind of different methods or methods of different complexity throughout this course. So starting from, well, first theoretical model. So each theory week will be concluded by a quiz. So the quiz is an electronic quiz with multiple choice, multiple answers questions, which will be available from Wednesday until Friday midnight. So in this time window, you have to take it. And the duration of a quiz is 1 hour and a half. So you do it at home. So it's an open book, obviously, so you can use side sources or information sources for solving this. The idea with the quiz is that while doing it, you still learn. So there are some questions that highlight the aspects that we, due to time limits, are unable to cover during the lecture. So I see a question in the chat. So let me see. Or you can unmute yourself and speak up.
Yeah, regarding this first theory week, you provided 4 sources, 2 of which are not reachable. The links link to point to a page which is not readable. So since the deadline is in 4 days, please fix it somehow.
Which one do you mean? So
The source on word embeddings points to nowhere, and the source on brain semantic maps points to nowhere.
Okay, I will double check, of course, and I will make available whatever relevant will be available and accessible. Okay. And then so the next week you will be focusing on the practical part. So basically, whatever we talked about this week, you will try while doing the lab on the following week, and the same goes on for other weeks. Yeah. Questions on that? Yes.
I think I read somewhere that the lecture slides are provided in this as well.
Yeah, they will be right after the class.
Fair enough.
Because that comes to another point. So some classes, like tomorrow and the day after tomorrow, they will be of whiteboard character. Well, I will write on a tablet. So I mean, they are not existing for distributing yet. So please come and listen. But then PDF will be available, of course, immediately after the class. But the topics are there, so you can start reading about it. Assessment criteria, just to be on the same page. We have 3 labs to do. So altogether, they generate 300 points, so 100 points each. And then they will be graded differentially depending on how many tasks you accomplished in each lab. So above 200 points is passed. But it's important that you do it in time. So there are 3 deadlines for each lab. So end of the corresponding practice week. For doing the labs, you are allowed to work in the group of 2. So you can form the groups yourself. And the important point is that when you do submission, so you write the names, name of each student in the group in the submission file. So the submission for the labs is basically a report with all the screenshots and in the intermediate steps, and as well as Python notebooks. That is executable by us. We'll, as you are many, not all notebooks will be checked, but we will do selective checks. Okay. Then of course, during the course of doing lab, so you will have questions. And here I'm encouraging you to assist each other. So for this, you have our main communication channel. So if I can jump to here. So how many of you have joined our Discord server? 1, 2, 3. 1, 2, 3. 4. Okay. Cool. Yeah, so the sooner you join, the better. Because this is the main communication channel. Why? Why not email? Let me see. Show you why. I guess I do it with every course. You see this magic number over here? You don't want to be part of of this pile. So please do not contribute increasing this count. So I just gave up at some point, but that's my own kind of shortcoming. Nevertheless, but seriously speaking, it just was proven. Oh, sorry. By many years experience that Discord is a very efficient communication channel. Well, it used to be Teams, but then so students normally dislike by some reason Microsoft. And after seeing it in several course evaluations, I said, "What the hell? Why do I need to see it in evaluation?" So I changed to Discord, and it was okay. Yeah. So now we have Discord. Yes, and in Discord, so we have different channels, and I can just show you again to demonstrate what kind. Does that? Oh, let me just show you a channel from the last year, maybe. Well, that wasn't very representative, but basically here you can put anything like screenshots, graphs, snippets of code, and then so let me see if this one is better. And then again, I'm encouraging you to assist each other. If you know the answers, and again, based on my experience, you do know the answer. I mean, some of you will know the answers sooner than others. It's okay to hint about the directions. So assist resolving this issue. We will intervene if discussion is stuck, of course, but I think it works very well when you assist each others. And by the end of the course, I will give extra points for most active helpers. So I call it good fellow points if needed. But again, it's on you to say, okay, I was very active, so please check. So and I need some extra points. So we solve it. And on Discord, we are normally very reactive, so maybe you shouldn't expect immediate answer during Sunday afternoon, but I mean, I check it quite regularly. Yes. Yeah. Quizzes. So this course has, as I mentioned so far, 3 quizzes by the end of theory week. So multiple choice, multiple answers type questions. But there is a question number 4. So this or quiz number 4, which migrated to this course from early instances where I had a seminar moment. And I think seminar moment is very useful. So so it's the part when you have to analyze a research paper and reflect on it. So the instructions are given in Canvas. Also, you will read them in PDF. And you have to present it in Zoom. So the presentation is scheduled sometime in December. So there is a whole week dedicated for this. And you have to attend presentations of others. And then you have to basically summarize it in essay type quiz. And you will be you will be awarded by 40% for just presenting, 65% for presenting and attending one seminar of others, and 90 points if you present and attend 2 seminars. Yes, is that clear? Cool. So then maybe last thing. The grading rules. So we have labs, quizzes, and a mini project. I will talk about mini project soon. So in all moments, you get a grade 3, 4, or 5, and here is the grading criteria for labs, depending on how many points you earned. And the course grading is like this. So 5 is all 5 in all moments. At most 1, 3 to get 4, and more than or equal to 2 3s in any of the moments gives you 3. Yes. Mini project is a very important moment in this course because you will be exposed to somewhat more complex learning problem. So as of last year, so I have a single task for all, but I give you freedom on what models to use in the mini projects. So while being here, I want to make a very important statement, so that not only in mini projects, but also in labs, it is strictly forbidden to use AI tools for implementation. I mean, we don't see it, what you use, but we see it afterwards in your submissions. I can give you like a concrete example. So Lab 6 is used to be the most complex lab. It is still, if you do it yourself. And there was a meaning with that. So Lab 3, the time series analysis, Lab 3. The idea is that you're given a research article and you need to implement an algorithm of a specific neural network type yourself based on the description. So if we are talking about randomly connected echo state networks, we will be talking about it towards the end of the course. And it is hard, so because it involves several skills. You need to understand the article. Also, it is rather detailed, so it's almost step-by-step instructions on how to do that, but it involves many concepts in it. Plus, you need to debug, you need to test, etc. And obviously, at some point, I started to notice that I mean, I see it clearly when people use AI or existing libraries. So just looking ahead for Lab 3, and it will be also written in the lab itself, you are not allowed to use anybody else's course or code or AI-generated code. So you should struggle yourself. And that is applicable to all other moments as well. Yes.
Python, you can use libraries fully, or it's also restricted to certain libraries?
Not libraries implementing, for example, echo state networks. So that's the whole thing. Otherwise, let me think.
Because there's a lot of libraries,
Of course, but that's the whole point. You see, the goal with this course is going inside the library, so to say. I mean that's yeah, I mean availability of frameworks. It's really cool. I mean it speeds up the development significantly. However, the knowledge of what's happening under the hood is sometimes very superficial in these people. So the idea is that we look into algorithms themselves. Just two examples. For example, self-organizing maps. There are libraries, of course, but you will be actually given a stub code to see how it is implemented. So sometimes you don't need to implement. So the only thing, the only place you have to do your own implementation is this echo-state networks. And since several years ago, there are libraries implementing this as well. But again, that's the point is to try to implement it yourself. Also for backprop algorithm, I give you one possible implementation, which is not framework based. So you will see all the details, all the matrix operations on the kind of on a feed forward, on a forward path, on a backward path. So you can understand the usage of different parameters. So that's the point. But it is not even asked to use framework there. So the only place where one possibly, no, two places. One place is the echo-state networks, and another lab, it's part of lab 2, which is about my research area, about hyperdimensional computing. So I will give a class on it. So now there are certain libraries implementing it, but again, the idea is that you would implement the algorithm, which is not complex in any way, given on a textual description on a research article. So 2 implementations from scratch you should expect. Okay. Yes, but then let me see. Maybe we should take a break before continuing with something else. So 5 minutes break. Yeah.
On site there.
Yeah.
I'm not sure where.
I will double check it.
Okay, because it's this one, and this one. No, this two. These are fine. But then
But actually, the only thing which matters, so I should mark it. I will double check the links.
Yeah,
So that is more for.
double check now.
I will double check it. You're right. It's the class.
I'm just wondering.
Yeah.
Are these supposed to be that I am supposed to look at this before the lecture, or is it after? What would you say I should focus on? First, is it the lecture, or is it? I mean, I would try to.
That's as a kind of supporting material. So I mean,
it's necessary, but it's not like.
No, so that's so this is information for I mean you can meet in the quiz, for example.
Okay, yeah.
Some of it.
Okay. And another question about the quizzes. How is this like if you have a longer time in regular?
You mean you need an extra time?
Yes. How long reporting it?
You can tell me, or you can try doing it. You can try doing it in regular time. So, for example, so it's 1 hour and a half.
Yeah.
And
It's
like 20 or 30 questions.
okay, so it's not 60, so it's one.
Huh?
It's not 60 questions, it's like. Is it 1 or 2? How many times can you do it?
1.
Okay, well, I can try and I guess I'll do as long as I can. If I don't answer the last questions, I will probably.
You can write me.
Yeah, and I can do this one again or something.
Yeah.
But then we will know after the first quiz how it goes.
Yeah.
Okay.
Mhm.
Cool.
Слава первым меня опубликовано. Не знаю. Но я смотрю, у нее только вот...
Она не опубликована еще, они только в пятницу получат.
Только в пятницу. Окей. Просто остальные опубликованы.
Yeah, that's right.
I have a question
Yeah.
because we have a lab, the session the 28th,
Yeah.
but I'm in a ESN trip this week.
Where?
I'll go to Lapland. Erasmus.
Yeah.
Yeah, there's a trip to the.
Typical, yeah.
Yeah.
So
Happens every year.
Yeah.
No, but I mean, it's you see, it's
because I'm away the 21st to the 27th, so the lab is the 28th.
yeah.
So I don't know if I'll have the things to do it, the knowledge to do the thing, or
I mean, try to do it.
no, but
then
to ask if there's any issue or there's some way, like, I don't know, to put it like made it like the 29th, because you said that the deadline is the deadline, so that's why
I mean, if there's some extra time needed in exceptional cases, I can of course make this request.
okay.
Okay, but there was like for this like the lab is not on the like the date of the 28th, or it's just a deadline, because it's like a really, it looks like a really like a lecture.
No. It's more. It's just a deadline. So
So the 28th is a deadline.
yeah. So
Okay.
you.
So all the like the lab days are no like
So
they're doing something
yes,
this week.
yes. I mean that's a kind
Okay,
of.
so along the week with all the sessions, you
It's
just
your
add
your
in the
own
knowledge
work.
and you can work.
Yeah, so you can.
Okay.
It's your own work.
Yeah. Okay. Then
On labs.
and the sessions are
And then
recorded.
this is just a deadline. Huh?
The classes are recorded.
Yeah, classes are recorded. Yes.
Okay, so next week we don't have like a meeting in person, but like the lab.
Yes. Well, there will be one session on Monday.
Okay.
Yeah. So,
Physically I will be here. Okay.
and in Zoom.
Okay. Okay, but okay. that
So
makes
it's an introduction session. So if you have questions, so the lab will be available. Well, maybe I even make it available immediately. So
Okay, now I understand. So, like, I mean, I'm not like, for me, it's like different. I go with like a later ESN trip, but then it's still time, because if I'm going on the Thursday, then I have like the whole week to like make the lab, and then it's fine.
yeah. Yes, you have the entire week to work in your own pace to complete the lab.
It's not like in the time in it software that they.
So we
I would ask if I can move the trip to the next session.
No, but it's, I mean, I counted that it should take you approximately, 50% of 1 week, like 3 days, maybe, to complete the lab.
Yeah, but if I also have to review all the videos and so on to know what you made in class, so I'll try to move the trip to the next week, because there's 2 trips. Maybe there's a slot on the other one, and I can move to the other one.
Yeah.
And if not, I'll email you or I'll send the message.
You always can send me a message on Discord, yes.
Also share.
Now it's fine, and it's good here now. Getting there.
And you also need this.
Yeah, on his.
Yes.
Now I started watching my picture. Yeah. Started watching but the German village is so sad. I want to fly. We're going on. And then there's Swedish yes. Because in German he has
Okay, dear colleagues, let's continue. Right now, what I want to start? I want to start narrowing down the scope of the problem we are discussing in this course that we are discussing today. So let's consider what we basically mean for by intelligent behavior. Yeah, if you want to formulate it like intelligent behavior, it refers to the actions of some biological intelligent actors. Like it can be humans, it can be mammals, sometimes even insects, or whatever. Yeah, and there are several essential characteristics that can define cognitive abilities. And one of the most fundamental of these characteristics is goal orientation. What it means? Our actions are guided by a specific goals, like since we are intelligent. So we can assess these goals. We can wait a second. Do I have? I need to double check that our colleagues from Zoom can hear us. Okay, guys, I hope you can hear us. I hope I will be loud enough. So, yeah. Wait, I'm so sorry. Yeah. So we can assess these goals. We can adjust our actions, our decisions, make some correctness as needed. And this ability for having a goal, it prevents us from acting some randomly or trying every possible alternative, since we're intelligent. Yeah, another important manifestation of the intelligent is our brilliant ability to reflect like some complex, detailed environments. And this brings us to main idea of our discussion. How can we connect our rich, like detailed environment? How we can connect it to this, like some higher level abstractions? Since like our environment may require vast amount of data to describe, and we need to reflect this requirement with a lot of data to our high-level abstractions. And like, shortly speaking, we want to understand how we can move from like our raw sensory data of like our complex real world to the domain, to symbols and symbolic reasoning. In this course, we will not focus a lot on solely only on symbolic reasoning itself. But on this course, we will establish like connection between physical environment and symbolic representation. Okay. Wait a second. Wait, let me check our Zoom. Nice. Okay, dear Zoom colleagues, if you have troubles, if you don't hear me clear, just like raise your hand or feel free to unmute yourself and speak loud. Okay. So what was I talking about? Yeah. So like in this course, we want to connection between physical environment and symbolic representation. And another, by the way, another interesting ability of aspect of intelligence is it's our ability to form ideas and abstractions, as you can see here in this slide. And honestly, for now, it's quite fundamentally, it's unsolved challenge for artificial intelligence. And also deep learning is not always helps us to solve these problems, because of course deep learning have achieved remarkable success. We all know it. But it still struggles when we need like when we need like derive some abstract reasoning, when we need to derive some symbolic reasoning. And neural networks are powerful, of course, but they still not fully capture how humans like for high-level concepts from limited experience. For example, this picture with chickens cave can be very hard for neural network to create a connection between like this set of pictures with symbolic abstraction of chicken. Yeah. And yeah, biological, if we look on biological actions like humans, they can understand and represent like some new objects, new abstractions from minimal information, like from minimal examples. Like here, we have like not so many pictures to derive the symbol, to derive the abstraction. And in contrast, our deep learning systems, they require like vast amount of data, and they still struggle with some like invariant representations. For example, they struggle in recognizing of object when it's slightly rotated or altered, for example. Yeah, and this is one of the first key limitations we face in neural networks. They often need many examples to learn, and whereas like even simple organisms like honeybees, for example, they can derive abstract concepts like only after a few exposures, only from few examples. And yeah, this is like one of the modern AI greatest challenges is like to achieve this kind of efficiency and flexibility, which even simple organisms, simple intelligent actors can provide. Yeah. And another important characteristic of intelligent agents is flexible behavior. Its ability to adapt based on environment. And in general, it involves having a plan while still allowing room for errors and adjustments. So in AI, this mechanism is also reflected in some of mechanisms like planning, adaptation, error correction, and like ideally when error happens, when some error occurs, intelligent system should not just simply fail, but instead the error information should refine its behavior. So intelligent system should adjust its reasoning. So this is quite often directly linked to learning. Maybe I think you have heard about learning already. Yeah, and learning, how we can call learning, it's just like the process when we continuously improve actions and decisions of our intelligent agent, and we base on the feedback from the environment. Okay, what else? Two final essential behaviors of intelligent agents are also ability to handle, we already mentioned it before, is ability to handle like large amount of knowledge, and also like derive new knowledge from the experience. And this is also reflects complexity of learning. We not just store information. We need to structure it. We need to navigate in this information. And we need to apply it effectively. Yeah. This is what I wanted to say here. What else? Yeah, by the way. And another key of learning, it's context dependent. And if you want to understand some phenomena, it requires like some understanding of environment and circumstances in which it occurs. And in many, by the way, in many machine learning tasks, like such like simple classification, for example, maybe you have already had this kind of examples, this kind of exercise. And models, they often fail when they face with data like outside of their training distribution. And their predictions like slightly different, and their predictions becomes unreliable. Yeah. And if we want to address this problem, our models must learn to like incorporate contextual information, allowing them to adapt and make more accurate. Yeah. Yeah, like all in all, we need to know how to make like meaningful decisions in unfamiliar situations when examples are different. Okay, and in example, it leads us to generic architecture of intelligence system, or like, let me just show it. Nice. To a generic architecture of intelligence system or intelligent agent, if you would like to call it. So our system receives input from environment through some sensory mechanisms, and it can in turn act upon this environment. And in this course, our focus is on the connection between like our sensory input and learning here. So we learn from environment and experience. Yeah, but still remains area which are not fully understood in the field of AI. Yeah. For example, when we deal with a process which never truly halt, we approach to a realm of algorithmically unsolvable problems. I mean, like the decision-making process has its continuous nature. And it raises like a question: can true artificial intelligence be achieved under these conditions? And this remains one of the most like fundamental and open questions in intelligent systems. Like, can our reasoning be limited? Can our reasoning be terminated? Yeah. What I wanted to say here. So, beyond buzzwords, AI touches like some algorithmically unsolvable questions. Yeah, like real intelligence, it requires, how to say it? It requires systems of complementary methods. It not requires a single models. I mean, yeah. So like we also face computational hardness in the practice. Have you ever heard, by the way, question for everybody, have you ever heard about curse of dimensionality? And also a question to Zoom colleagues as well. No, you have never heard about it. Okay, curse of dimensionality, briefly speaking, is like if number of features grows, the data becomes sparse. And like volumes explode, like distances between data, they lose their discriminatory power. This I think all will be shown in next lecture, not in next lecture, in Wednesday lecture. Yeah, and like sample computation needs, they rise sharply. So like your data is your number of features grows, data becomes sparse, and so complexity is growing, computation is growing, and generalization is also, generalization degree is also growing with higher dimensionality. I mean, like, if you increase the feature amount of feature describing something, your dimensionality is exploding. No, I don't want to talk about this. So, also there exists 10 complexity, and we can discuss it like using two simple algorithms here as example. Algorithm 1, here we have like, it's linear tasks. It's linear task. It's talking about like 5 million operation to process n bits number. Algorithm 2 checks checks whether an n-bit number is a prime. And it requires roughly this amount of operations. If you don't trust me, you can check on yourself. And complexion is growing exponentially. And we have two machines here, one gigahertz and one terahertz. So we see that exponential algorithm is quickly becomes just infeasible because like when n increases. Yeah. And this example shows us how computation time of our models can explode. Yeah, when even models is grown, for example. And in machine learning AI, of course, this is crucial. Like dimension rises, computational cost rises, and you have, I think, in lab 2 or in lab 1, yeah, you will be able to investigate it also in your labs, like when you can see how computational costs are growing. That's why also in our lab, I would recommend you to include kind of like execution monitors. Have you ever worked with Jupyter, by the way? Right, raise your hands who have ever worked. Okay, for other participants, it will be a big surprise, but for sure. So, I recommend you even to Jupyter, don't rely on standard Jupyter tools. Add execution monitors, like in your code, printfs or whatever, just to track progress. And it just like to help you to understand like what's happening with your algorithm. Yeah. So add monitors. And another aspect. Okay, I think. Why did it become? Sorry. What is the?
It will disappear. It will disappear.
Okay.
Self.
If it will disappear, and then. Okay. Yeah. Another aspect is partial complexity. Like each data point usually in your observation is like a set of features or variables which describing like some aspect of your system. And there is dramatically difference between like, for example, like 10,000 observations of in three-dimensional space. Like, for example, you're describing point in three-dimensional space and 100 observations in 50-dimensional space. And in low dimensions, like large number of samples can describe the phenomenon, like density describes the phenomenon. Like you can achieve good approximation, but when your dimensional grows, that data becomes sparse and like, so even if you have like only thousands of samples, they may cover only like tiny portion of the space. And this is the essence of curse. It's called curse of dimensionality. Number of feature grows, the volume of the space expands exponentially, and unfortunately, data density drops dramatically. You cannot describe your environment with this amount of data. And this is one of the reasons why deep learning models, why they require massive data sets. They just need enough examples to cover like whole environment, the whole space. Yeah, because we need to represent like some complex phenomena, we need a lot of data for training. Okay. In your first lab, you will have task to like nearest neighbors classifier. This topic will be covered in Wednesday lecture, as far as I remember. Yeah. Tomorrow. Okay, tomorrow and in Wednesday lectures. It's a long lecture, remember it. Yeah. So please join the lecture. So what is Canier's classifier tasks like? You have you have a set of labeled samples and classifiers in a query by the closed move point under a chosen distance. And it will be explained. If you haven't touched it, don't worry. Like everything will be explained very briefly tomorrow. Very deep tomorrow. Yeah, like, and in low dimensions, modest memory, it can approximate like a distribution well, but in higher dimensions, you will see it in your lab. You will see everything in your lab. The amount of required samples are growing exponentially. Like distances concentrate nearest point are far and like nearly undistinguishable. And you will also notice that in your first lab, performance of will degrades when dimensions are growing. And you have vast data and careful people. You have to have vast data and careful pre-processing of this data. Yeah. Short spoilers to your lab. Please don't be too scared. Yeah, so like take a wait for a first lab, just like short teaser. Its classifier is simple as strong, but when amount of dimensions is growing, you need many more samples. Or like you need to reduction of matrix learning or something like this. Yeah. What else? What else do I want to choose? Okay, and now let's talk a little bit about differences between learning in the final part of our lecture. Talk a little bit about difference between learning and memorization. Sorry. Memorization is kind of learning, a varied learning mechanism. Like for example, in your teaser for lab 1. Like Canier's classifier, it relies on like stored examples, and it relies on kind of analogical reasoning. But the problem in this kind of memory-based learning, it's lacks of generalization. Like it doesn't move like from like raw inputs to a model or to a rule. You cannot derive rule from like a set of memorized examples. Yeah. And usually what we want to learn, when we want to seek in a learning, is precisely like this abstraction step. We want to have ability to derive patterns, like, for example, if, then, and the rules, which can help us later to apply for examples. Yeah. So memorization helps. You will try it. You will touch it in your first lab, but unfortunately, for true learning, is not sufficient. Yeah. You can also ask, like, okay, we can just memorize rules, and unfortunately, of course, you can memorize rules, but usually it's unfeasible. Usually, it's like deep learning and AI agents are solving tasks when all rules, like memorizing rules, is just unfeasible. And even if you have a huge rule list, it cannot be generalized. And what else? So, like in general, our goal, we want to build models, and if it's possible, if we are lucky enough and if we are strong enough, we can learn like kind of meta rules from our set of data. We can derive these meta rules, and then we can explain like why the phenomena behaves as it does. Yeah. So in this course, to summarize, we focus on supervised and unsupervised learning. Do you know what's the difference? Okay, after the course you will be able to answer. And unfortunately, reinforcement learning is out of scope for this course. Is that everything I wanted to tell? Yes, I think it's everything I wanted to present today.
And now I will give you some pre-taste of what we'll be covering tomorrow and the day after tomorrow. So maybe going deeper into the type of models that we will consider. So. See. And by the way, I updated the links in Canvas, so now they're all functioning. Oh. Yes. Let's see. We start screen sharing. All right. Let's talk about the landscape of AI or AI in the domain of learning. So. So as I said before, so we will be focusing on the learning functionality, learning from data, and as Tatiana has mentioned, so being able to understand your data is the core for selecting a model. And so first question you may ask yourself whether you can define certain characteristic properties of your data or not. So what do I mean here? So we will be talking about, starting from tomorrow, we will go in a kind of very fast forward manner from basics of machine learning to more advanced models. But in either case, we are talking about an agent on the one hand, and environment, and specific phenomenon of the environment. And we sense this environment through sensors. And so this environment, so we conceptualize inside an agent through a set of characteristics. So if S is your sensor, so it can be characterized through a set of characteristics. So X1, X2, Xn, right? So what is this axis? So, and this is really depends on your sensor, what you use to sample the environment. So, and in general, we talk about these variables through which we describe a given phenomenon as features. So those are features. And what we will be talking about again, so that's important to understand. We will be talking about a set of variables describing a phenomenon, and normally we refer to this set as vector of features or feature vector. So this S is and now I want to link to what Tatiana has said. Now, if you can call to your memories this about basic geometry. So we have a many-dimensional space, really a geometric object. So in which whatever we sample, whatever phenomenon we sample appears as a point in this many-dimensional space. In the simplest case, if we just sample a 3D environment just with 3 characteristics, so I don't point to any real one. So that would be coordinates in the space, like 3 coordinates. Real phenomena, they are much more complex. For example, you have a camera sensor, again, maybe not real to begin with 28 by 28 pixels resolution. It's very lousy camera, I would say, compared to telephones. But together, so you have how many pixels? 28 by 28, right? 784 pixels. So through which you look at the world. So at in a given phenomenon. So basically, you project your phenomena into or onto 784 dimensional space. So whatever you point your camera on will appear as a point in the in this many-dimensional space. Jeff Hinton, who is behind the inventor, he's inventor of the backprop algorithm. He said, it's very easy to imagine high-dimensional space, more than 3-dimensional space. You know how? You close your eyes, you imagine 3-dimensional space, and then loudly say 1,000. So then it helps. Well, actually, it doesn't. So it's in many cases it's rather impossible to directly visualize this space. It is sparse. Sparsity in a way that you can imagine number of possibilities. So the number of total points and in this many-dimensional spaces, and that what is meant by availability of a sufficient number of examples. So the more examples you have, the more you start to form certain shapes in that space. So literally all machine learning methods you can kind of down project to 3 dimensions. So only with 3 variables, like take any 3D room, and then the idea about sparsity or being enough samples for a successful machine learning task is really forming certain shapes in geometric shapes in this space. In mathematical terms, we talk about manifolds. So when you cannot kind of describe a shape as a kind of cube or square or something, so it is a manifold. And the thing is that all phenomena, they are very complex surfaces in this many-dimensional space. And the idea of any learning task is to is either to characterize the surface, to be able to explain. So, for example, how number 7 is transformed, or how number 1 can be transformed into number 7. So, because I mean they're pretty much similar to each other, or how to draw lines between them, or certain borders separating this constellation of samples. That's a typical classification task. But again, so we are talking about features, but then here we have two alternatives. We have cases where features can be well defined. So they are maybe categorical features. So certain, for example, if you characterize animals, you can say, okay, so an animal may have 2 or 4 legs, then number of eyes, whether they may have feathers or not, and such. So these features are kind of easily understandable, or they're not easily understandable, they are well defined. So categorical features. You can extract, for example, using classical methods, certain characteristic shapes of a continuous signal. And again, as soon as you can extract these characteristics from a phenomenon, then we talk about well-defined features. On the other end of the spectrum, we have features where you have cases where you looking at data, you cannot see any obvious characteristic, and this is a typical case, for example, for images. So images are just pixel intensities, or what is it? Continuous signals of complex shapes. So depending on whether you can, where you do have well-defined features or not. So this is the first kind of checkpoint for you, which model to choose. So if you take the whole class of machine learning models, so as I said, 2 main branches are whether you have well-defined features, or you have no obvious features in or in many cases we talk about complex data. Right? So if you do have well-defined features, and well-defined meaning that there are standard routines on extracting, on understanding these features. Here we talk about class of algorithm called classic, which normally attributed to classic machine learning methods. And here, so this class in itself, depending on the task, at hand, it contains methods for, say, supervised learning, and unsupervised learning. Unsupervised. Supervised is when you have ground truth about the phenomena that you try to learn, versus unsupervised, where you have no idea what the data is and you try to figure out the internal structure of it. So here in the supervised branch, you have tasks like classification. And if you do have a classification task, so you want to decide whether sample A belongs to category A or B. So here you have such methods as KNN, so again, lab 1, as Tatiana said, or very useful technique, which is called decision trees. Why useful? Because it is explainable. when trained, so you can trace why certain decision, how certain classification decision is taken. Another alternative for a task in the supervised domain could be a regression, so prediction of a next value in a row. So regression. So here we have linear, polynomial, and ridge regression. So again, classic machine learning techniques widely used nowadays. So when people in industry talk about AI, they in the first place many times mean these classic methods. Why? Because they are computationally simple. So ridge regression is based on matrix operation, vector matrix multiplication to determine a class. So to train the ridge regression, you just need to take an inverse matrix inverse, so to say. Decision trees, so they like explainable moments, and again, so the inference phase is very fast. So in many cases, when and again, in many practical cases, you can extract features. So you opt for these techniques as they are faster and simpler. Then again, so this reinforcement stuff, so which we do not talk about. RL. And an important class of classic methods in the unsupervised branch. So here we have tasks like clustering, or feature, or dimensionality. Reduction. So, can you give me an example of a classic clustering algorithm? Huh? dbScan, k-means. K-means. Again, for practical usage, when you talk about to people doing business analytics or data analytics, so in many cases, for them, AI is about understanding how data is clustered. So the clustering is a very important way to understand the data. Dimensionality reduction. So this curse of dimensionality is a problem. It's a problem that first, of course, you can describe a phenomena through thousands of features. So say now you have high resolution camera, so you have plenty of features, right? But then the more dimensionality you have, so the more complex your model will be. So on the other hand, so you should understand that not all features are significant for a classification, obviously. And again, in mathematical terms, so you want to look at the features which are more significant. So basically, which expose sufficient variance for specific classification task. And there are techniques like principal component analysis, singular value decomposition that aim at reducing or transforming your data in a smaller dimensional space in which all features are significant. So you can build a simpler model. So that techniques are used everywhere. So the current landscape of AI in what matters learning is about applying different techniques together. So even when you talk about neural networks, you do plenty of pre-processing, including dimensionality reduction, before feeding it into the algorithm. So basically, on the path with complex data, here we have our artificial neural networks. So we have artificial neural networks. And again, so the tasks are same. So we have unsupervised learning and supervised learning. So in the unsupervised, that's what we will talk about here. We have a special, and here again, so we can link ourselves, and now I will finish very soon, to this different, to the ever-going discussion about how to implement AI functionality, whether using symbolic kind of reasoning or neural network based. So basically understanding how brain works and such. So that's so the whole domain of ANN appears as a reflection or as an attempt to understand how intelligent functionality is implemented by biological brains. But tasks are exactly the same as in the upper branch. So in the unsupervised learning, so you will learn the algorithm which is called self-organizing maps, or SOM, self-organizing maps. So in the classification, in the supervised domain, so here we have our beautiful multi-layer perceptron, so with the backpropagation algorithm, and all the deep learning stuff. So all deep learning stuff is here. So convolutional neural networks and such, they're here. But also, whenever you work with a time-dependent case, so that's basically your features, so they're not static, but they're rather dependent on how they co-occur in time. So you need a different class of networks, so which is called recurrent neural networks. So here we have that's what you will work with echo state networks or LSTM, long short-term memory. So we will talk about it in the module dedicated to time series classification. So tomorrow we start with the somewhat with the upper branch a little bit. Again, diving into the details on how to work with data. So what is important with respect to choosing the distance metrics and such. So there will be some mass exposure, and eventually we will end up here in this domain. So that's it for today. Thank you.